Hey everybody, Mr. Dickin here. In this video lesson, we're going to be introducing a whole bunch of parent functions. So we're going to be talking about 6 different parent functions that you guys will be expected to know just the basic shapes and behaviors of. And then we're going to talk about how we can shift them. And these are called transformations. Anytime you have a function and you're changing it somehow, whether it's a shift or later on a stretch or a rotation or a flip, that's what's called a transformation. So let's start talking about our basic parent functions. All right, so we'll start off with a constant, and then here it's called the identity, but we're most likely going to refer to it as a linear function. First things first, though, constant functions. A constant function is anytime you have y equals some number. So in this case, it's y equals 4. Remember, the f of x behaves just like a y. Well, if I wanted to graph that, that would just be a horizontal line at 4. So right there, boom. There's a constant function. Next up, an identity function, or a linear function, is going to have some sort of a slope to it. Now, if we think back to what we know about linear functions, we typically dealt with y equals mx plus b, slope-intercept form. Well, if you look at this function here, it's technically slope-intercept form. It just has a slope of, well, technically a 1, if I really wanted to put it there. It's got a slope of 1, and then a y-intercept of 0, if I really wanted that. So when it comes time to graph that, if I've got a y-intercept at 0 and a slope of 1, I could just kind of plot a bunch of points till I'm satisfied there, and then throw my line graph across them, and boom. There we have the identity function. The next two are going to require a little bit more dexterity from my part, so I apologize in advance for the lack of penmanship. I say that all the time, but this time it definitely holds true. Next up is a quadratic. Quadratic is anytime you have a variable squared, so x squared. Now, some of you might remember quadratic functions. When we graph them, they create U-shapes. That shape is called a parabola. Now, if I wanted to try to get specific points for this, I could envision a table, right? A little XY chart. And let's go -2, -1, 0, 1, and 2. Just keep those values nice and easy. So for each one of these, I'd do -2 squared. And when I do that, it's -2 quantity squared. If you were to type this into your calculator and you forget to have parentheses there, it's not going to give you the correct answer. So please keep that in mind. All right, -2 quantity squared, that's going to be a positive 4. -1 squared is 1, 0 is 0, 1 squared is 1, and then 2 times 2 is going to be 4. So here I've got a set of points that I can start plotting. So we had -2, comma 4, so -2 up 4 would be right there. -1, comma 1, 0, 0, 1, 1, and 2, 4. Now our table didn't go this far out, but just since we have room, I'm going to go ahead and plot. If -3 was my x value, that would go up to a positive 9. So I'm going to plot some extra points there. All right, so now here's the moment that I was warning you about. My dexterity is going to be put to the test. We're going to try our best to connect them. Woof, not my best work. A couple points here. First and foremost, make sure you're not doing a sharp corner down here. We want that to be a nice rounded curve. This point right here on a parabola, that's going to be called your vertex. So whenever we start shifting these things around, we're typically going to pay attention to where that vertex goes. The next thing I want you guys to notice is that there's this symmetry aspect. If I were to kind of pretend that there was a mirror straight down the middle, everything on the right side of that mirror is going to be the exact same as the stuff on the left. So this is what's called the axis of symmetry, and you'll notice that that goes straight through my vertex. So when you're looking for shortcuts to graphing these, really if you just kind of plot a few points over on one side of the vertex, you can copy your own points over to the other side, save yourself some time. The next thing I want to discuss is a little shortcut here. Instead of counting over and trying to plot out, all right, 2, 4, 3, 9, quadratics use a pattern where if I go one step out, I'll go one step up, then one step out, then 3 up, and then the next step out, I go 5 up. So by no means is this like an official math theorem, but I call this the 1, 3, 5 pattern. So if I have a vertex for a parabola, and I just want to graph extra points, assuming it hasn't been stretched, I just go up 1 over 1, up 3 over 1, up 5 over 1. If we had more graph, I could go up 7 over 1, and that pattern would just continue. All right, next up, the absolute function value. The definition of absolute value. Most people think it just takes numbers and makes them positive. Well, yeah, I mean, that's close. The actual math definition is it's the distance from 0. If you think of a number on a number line, how far is it from 0? And since distances are always positive values, that's why we get that behavior. Now, I'm going to go through and do my standard -2, -1, 0, 1, and 2. And if I'm thinking absolute values here, it's just going to be making those x values positive because -2 is 2 units away from 0 on a number line. When it comes time to graph this, we'll have the vertex, it's technically what's called a cusp, since it will be a sharp corner, at 0, 0. Then we go up 1 over 1, up 1 over 1. If I wanted to, I could continue going this way, because the absolute value of 5 is 5, the absolute value of 6 is 6, so on and so on. And it's going to behave the exact same on this side as well. You'll notice there's a pretty good similarity between parabolas and absolute values in the sense that they both have a symmetry aspect about them. Holy cow, I completely missed. Woof. Now, unlike our parabola, where the curve was getting gradually steeper and steeper and steeper as it goes out, you'll notice the absolute value just stays at a constant up 1 over 1, up 1 over 1, up 1 over 1 as it goes. All right, on to the last two. Cubic and square root functions. So cubic function is when you're going to have your variable cubed or raised to the third power. Well, to see what this looks like, I'm going to use my standard easy x values, -2 all the way up to +2. And if I'm thinking about what is -2 cubed, if I did -2 to the third power, that's -2 times another -2 times another -2. Well, that would result in a -8. If I did the same thing with -1, I'd get -1, 0, 0. 1 is 1, and then 2 would be a +8. So again, we have a similarity here where if I'm looking at my quadratics, I see 4 and 4, I see 1 and 1, and then the 0 is kind of the middle. Absolute value, I see 2 and 2, 1 and 1, 0 is in the middle. Over here, very similar, I have 8 and 8, 1 and 1, and then 0 in the middle. The only discrepancy here, the only difference I should say, is that now we have some negatives. So this won't be completely symmetric. All right, let's graph this. Okay, we have 0, 0. I'll start in the middle. This is what's going to be called the inflection point of the graph. You don't really need to know that until calculus, but I figure I'd tell you now, because why not? And we had 1, 1, and then we had 2, 8. So 2, 8 would be over here. And now we have the negative side of that. So we have -1, -1, and then -2, -8. Now when we draw this in, it's going to make, I'll draw it over here just so I don't have to worry about points. It's going to make a little curvy graph. Ooh, that was pretty rough. So now what we're going to try to do is fit that to our points. I'm not going to lie, you guys, I'm actually pretty proud of that one. Pretty stoked about that. So that is the shape of all cubic functions. It might get moved around, it might get flipped upside down, but that is the shape of all of them. All right, next up is a square root function. We're taking the square root of x. Now here's where we want to be kind of careful with what values we choose. I don't want to just go through and do -2, -1, 0, 1, and 2, because if I try doing the square root of 2, I'm going to get 1 point blah, 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 and I don't know how to graph that cleanly. So what I'm going to do is I'm going to choose values that I know for sure have clean square roots. Well, I know 0 has a square root. I know 1's got a square root. 2, no. 3, no. 4 has a square root. 5, no. 6, no. 7, 9 would be the next one. So basically, I'm just looking through all the perfect squares. You'll notice there's no negatives here because we don't know how to take the square roots of negative numbers just yet. All right, so let's see. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. When it comes time to graph, we'd plot our points out. So I've got 0, 0, 1, 1, 4, 2, 9, 3. And to the best of our ability, we're going to connect those. You'll notice this graph has a clear, defined endpoint because there is no other portion of it, since we can't take square roots of negatives. And if there was a graph down here, well, then it would fail the vertical line test. It wouldn't be considered a function. So this is going to be the shape for square root functions. You'll notice square root functions behave awfully similar to quadratic functions, but it's almost as if we took a quadratic function. Let me see if I can steal a bit here. It's almost as if we took a quadratic and then flipped it on its side. So that's going to be the shape of our square root. Another thing to keep in mind here and kind of notice is that since it's really behaving the exact same as a quadratic, it's just kind of flipped, it's still going to follow that whole 1, 3, 5 pattern that I mentioned earlier, only this time it's always going to go up 1, and then over 1, up 1, over 3, up 1, over 5, if I had more room, up 1, over 7, so on and so on. All right. Now let's start transforming these things. When we transform them, we are going to have vertical shifts and horizontal shifts. So if I had a graph, a vertical shift might move it up or down, horizontal would move it left and right. The way to tell is if you have a constant value added or subtracted to the outside of your function. General rule of thumb with these: if you have a positive, it's going to move it up. If you have a negative number, it's going to move it down. This will be true for every single parent function. So as I go through, I'm really just looking at the constant numbers on the outside of the function. I don't particularly care what type of parent function it is. I'm just looking at that constant value outside. All right, so the first one, it's going to go down 6 units. Number 2, since it's a positive 1, we're going to be going up 1 unit. Next, we're going to be going down 4 units. And last, we're going to be going up 5 units. Not too difficult there, right? So anytime you have a number outside of the function, a constant doing its own thing, not related to the x at all, that's going to control up and down movement. Well, now let's talk about horizontal shifts. Horizontal shifts take place inside of the function, so it's going to be right next to your x value. It's going to be buddy-buddy with the x. And this one is almost counterintuitive to what you might think. If you have a plus or a positive, it's actually going to move your graph to the left. If you have a minus some number or a negative value, it's going to move it to the right. So it's kind of counterintuitive for some folks. Another important piece here is it says the coefficient, leading coefficient of x has to be 1. So no numbers attached to the x, no negatives, no nothing. All right, let's go through. Here I'm seeing a minus 3. Well, minus means it goes to the right, so it's going to go to the right 3 units. Number 2. We've got a negative sign on the x. No me gusta. Don't like that one. So we'd have to factor out a negative 1. And then I'm left with an x plus 2 to the third. I'm allowed to do that factorization because we have an odd exponent there. So now, since it is a plus or a positive number, it's going to be going to the left, and it's going to shift to the left 2 units. Number 3 shifts to the left 5 units. And number 4 is going to go to the right 4 units. All right. Let's try graphing. Number 1, I've got x minus 2 quantity squared minus 3. All right, the fact that this is squared, that means it's a quadratic. So I'm anticipating a parabola. My parabola normally starts off at 0, 0, but it's going to be shifted around, so I'll have to keep track of that. And then, let's see, the minus 2, it's going to go to the right 2, and it's going to go down 3. Okay. So I have a parabola that went to the right 2, and it went down 3. So it normally started off here. It's going to go right 1, 2, down 1, 2, 3. There's going to be my vertex. Now I could make a table of values, but honestly, I don't know about you guys. I'm feeling kind of lazy. I'm 17 minutes deep into this thing, so I'm going to try to expedite it. I'm going to use that 1, 3, 5 pattern. So I'm going to go up 1 over 1, up 3 over 1, up 5 over 1. Then I'll mirror it to my other side and call it a day. So there's the 1, there's the 3, and just for funsies, there's the 5. I can mirror those on the other side to get my freebie points. And now I connect the dots. I've got my awesomely drawn parabola. Yay. All right, next one, number 2. We have x plus 1 quantity cubed plus 2. All right, x plus 1 cubed plus 2. So that was a cubic. That was one of those shapes. And according to my values here and here, we're going to be going left 1 and up 2. So my inflection point was normally at 0, 0, but we're going to go left 1 and up 2. There's my new inflection point, and that will behave like the 0, 0. If I think of my normal graph, we had the 0, 0. Let me zoom in a bit here. With the 0, 0, the 1, 1, and then the 2, 8. And then the negative versions of those. All we're going to do is take these points and shift them left 1 and up 2. So I'm going to start here at the inflection point. So if I go left 1 and up 2, it's going to be right there. So again, I took this point, left 1 up 2. I'll do the same thing up here. Left 1 up 2. So there's part of my graph. And now the other part is just going to take place down this way. All right. Let's see. In the interest of time, I'll do just number 4. Number 3, you can get the answer to that on the digital copy here, or you can follow along. It's just going to be just like number 1, just different shape. All right. So number 4, we have a square root. So it's going to have a set endpoint and then kind of look like the top half of a parabola. that was tipped over. According to this, we're going left 4, we're going up 1. So remember, numbers inside the function control left and right. Outside the function, control up and down. My vertex was normally at 0, 0, but it got moved, left 4, up 1. So my new vertex, or the endpoint, is going to be left 4, up 1 right here. And then I'm going to follow that 1, 3, 5 pattern. So go up 1 over 1, up 1 over 3, up 1 over 5, and Shazam. There we go. All right. Sorry for the lengthy video. But you guys know the drill. If at any point you have any questions, please do not hesitate to reach out. Send me an email if there's anything I can do to help. And as always, folks, good luck, have fun, be safe, roll tide.